Have you ever wondered how we can talk about something like chance with perfect mathematical logic? Well, that's exactly what we're going to do. We're going to build from the ground up the simple core rules that let us find beautiful order in the chaos of randomness.
So here's the big question, right? How in the world can you use math, this thing of certainty and rules, to create a system for something that is, by its very nature, unpredictable? It sounds like a total contradiction, but that is precisely the genius behind the foundations of probability.
All right, here's our roadmap. First, we're going to map out the entire universe of what could happen. Then, we'll learn how to zoom in on the specific things we actually care about. After that, the really crucial part, the 3 unbreakable rules of chance. We'll snap it all together into one elegant system, and then we'll see why this stuff isn't just for rolling dice, it's for understanding pretty much everything. So our journey has to start somewhere, and it starts with a simple idea called a random experiment. This is just any process where we know all the possible outcomes ahead of time, but we just can't predict which one we're going to get on any single try. Flipping a coin, rolling a die. You know what can happen, you just don't know what will happen this time. Okay, the first and maybe the most important step is to define our entire universe of possibilities. In the language of probability, we call this the sample space. You'll usually see it written as a capital S or the Greek letter omega. And it's really simple. It's just a complete list of every single possible thing that can happen. That's it. Nothing missing, nothing extra. Let's make this real. For a standard 6-sided die, the sample space is just the set of numbers 1, 2, 3, 4, 5, and 6. This is our complete map. When you roll that die, you are guaranteed to land on one of these 6 outcomes. Now, for this whole system to work, our sample space has to play by 2 very strict rules. First, the outcomes have to be mutually exclusive. That just means only one of them can happen at a time. You can't roll a 3 and a 5 on a single die at the same time, right? And second, the list has to be collectively exhaustive, which is a fancy way of saying it has to include every possible outcome. There can't be a secret 7th option. Our list, 1 through 6, totally nails both of these. Okay, so we've mapped out our entire universe of outcomes. But let's be honest, we're usually not interested in everything that could happen. We care about specific results. And this is where we need to define an event. An event is really just any smaller group or subset from our big sample space. You can think of it like taking a highlighter to our map and just marking the outcomes you're interested in. It could be just one outcome, or it could be a whole bunch of them. So, sticking with our die, let's say we define an event, we'll just call it event A, as rolling an even number. All we do is look at our sample space and pull out all the outcomes that fit that description. So that gives us the set containing 2, 4, and 6. See? This new set A is just a little collection of outcomes taken from our original sample space. And we can even get a little more specific here. If our event is just a single outcome, like the event of rolling a 5, we call that a simple event. But if it has more than one outcome in it, like our rolling an even number example, we call that a compound event. Simple as that. All right, we've got our universe of outcomes, the sample space, and we've got our points of interest, the events. Now, we need the rules of the game. What are the fundamental laws that tell us how to assign probabilities to these events? Well, back in 1933, a genius Russian mathematician named Andrei Kolmogorov laid them all out. We call them the Axioms of probability. And you know what's amazing? There are only 3 of them, and they are so elegant and simple. Let's walk through them, starting with number 1. First up, the axiom of non-negativity. This just says that the probability of anything happening has to be 0 or bigger. It can't be negative. And that just makes sense, right? You can't have a negative 20% chance of rain. The absolute lowest you can go is 0, which just means it's impossible. Okay, on to rule number 2. This is the one that basically sets the scale for this entire system. The second axiom is called normalization. This one says that the probability of the entire sample space, meaning the chance that something from our list of possibilities happens, is exactly 1, or, 100%. This is so important. It basically says when you roll a die, one of those 6 faces has to come up. Something is guaranteed to happen. The total probability is locked in at 1. And that brings us to the third and final rule. This is the one that tells us how to combine probabilities together. Axiom 3 is additivity. And what it says is, for any 2 events that can't happen at the same time, remember, mutually exclusive. The probability of A times or B happening is just the probability of A plus the probability of B. That's it. If you want to know the probability of rolling a 1 or a 6, you just add their individual probabilities together. Simple.
So, there they are. The three pillars: non-negativity, which says probabilities can't be negative; normalization, which says the total probability is always 100%; and additivity, which gives us the rule for adding probabilities of separate events. The craziest part? From just these three simple ideas, the entire world of modern probability theory can be logically built. It's incredible.
So, we've defined the outcomes, we've defined the events, we've defined the rules. Now we can finally assemble all these pieces into one complete formal structure. And this is what it looks like, the probability space. It's the whole shebang. First, you've got omega, that's our sample space, our universe of all outcomes. Then you have F, which represents all the events we could possibly be interested in. And finally, you have P, the probability measure. That's the engine that runs on our three axioms to assign a number, a probability, to every single event. Okay, so what? Why does this matter? Why go through all the trouble of building this formal structure? Because this is what lets us take probability out of the casino and put it right into the heart of modern science. See, before Kolmogorov, probability was kind of a messy collection of good ideas and clever tricks, but it wasn't always consistent. What he did was give the world a rock-solid foundation, a consistent language for uncertainty that everyone could agree on, trust, and build upon. And believe me, people have built on it. This exact framework, sample spaces, events, and axioms, is the mathematical engine humming away underneath artificial intelligence, quantum mechanics, the entire financial world, and all of modern statistics. It is literally the bedrock for how we think about uncertainty in almost every complex field you can imagine.
And that just leaves us with this one kind of mind-blowing thought: the incredible complexity of AI, the weirdness of quantum physics. All of it rests on these three incredibly simple, almost obvious rules. It really makes you wonder, doesn't it? What other huge complex systems in our universe are being governed by foundations that are just as elegant and just as simple?